Pulleys and Wedges, Type 4 inclined plane. So in 2003 we were given a block of mass 4 kilograms on a rough inclined plane. So important to underline that the plane is rough, and it's inclined at an angle of 60 degrees to the horizontal. It is connected by a light inextensible string which is passing over a smooth light fixed pulley. So again, smooth meaning no friction with the pulley, and inextensible string meaning that there's not going to be any bouncing with the 8 kilo in the string causing simple harmonic motion. Okay, we have it connected to an 8 kilogram mass which is hanging freely under gravity, so it's not in contact with any surface. And then we're given the coefficient of friction between the block and the plane is 1/4. So in other words, that's our mu. We're told the system starts from rest, and the block is a distance of 2 meters from the pulley, and the 8 kilogram mass moves vertically downwards. So if we draw all our forces acting on it, just so we can get an overall picture of what's happening here in the diagram, well, we have common string, so therefore common tension, and tension always acts away from the block. We'll have gravity acting on the block, so we're going to have our weight acting down, which is our 8g, and we'll also have weight acting down here for the 4 kilogram block, which is 4g. So clearly we can see we're going to have to resolve our weight there. Because the block is going to accelerate up as the 8 kilogram accelerates down, then we're going to have friction acting away from the direction of the motion. So we're going to have F there as well. And of course the 4 kilogram block is in contact with the surface, so we're also going to have a reaction force. So now we have an overall picture of what's going on. Well, in order to find in question 1 the tension, well, what we're going to need to do is set up each of our particles and look at the forces acting on each of those in separate diagrams, and then set up our simultaneous equations. Okay, so let's look at the first block. So I'm going to start with the 4 kilogram block. And with the 4 kilogram block, we're going to have to resolve. So I'm just going to look at this from a resolved perspective. So we have it in contact with the surface. So I'm rotating my diagram there. So we have our reaction force acting up, and we're going to have to resolve our weight. And it's accelerating to the right, so we said we had tension, and we also are going to have friction. Okay, so resolving our weight. So let's just do this to the side here. So here's our block. We have weight acting down, and therefore if I'm resolving it, I have my parallel and perpendicular components. And of course then the angle is 60 degrees there. So therefore that means that that would be 60. This one here would be 30, which makes this one 60. Okay, so therefore this is the opposite, this is the adjacent, and this is the hypotenuse. Sorry, that diagram's a little bit small there today. Okay, so therefore the opposite side is always going to be our sine. So sine theta equals opposite over hypotenuse. Therefore the opposite is equal to the hypotenuse times sine theta. And the hypotenuse in this case is our weight. And our weight is our 4g sine 60. And then the adjacent, well, cos theta is equal to the adjacent over hypotenuse, and therefore the adjacent is equal to the hypotenuse times cos theta, where the hypotenuse is the weight, 4g, times cos 60. And of course, cos 60 is a half, so therefore that can be written as 2g. And sine 60 is root 3 over 2, so root 3 over 2 times 4g gives me 2 root 3g. Okay, so now if we're looking at our equations, well, what can I say? Well, the block, 4 kilogram block, is not lifting up or down off the plane, and therefore the vertical forces must be equal and opposite. So in other words, we have our or must equal our 2g. In other words, the up equals the down. in terms of our forces. And we also know then that friction is equal to mu times R. Now we were given our mu was a quarter, or we've worked out to be 2g. So therefore the frictional force is basically g over 2. So if I'm then looking at my net forces in the direction of the plane, well, that can be found using F equals ma. So I can see there the forces to the left and the forces to the right. Well, because it's accelerating up the plane, my leading force then is my tension, minus the opposing forces, which is our force and our resolved weight. So our force, we've said, is g over 2, and then the weight in the direction of the plane is 2 root 3g, and that equals the mass, which is 4 kilograms, times the acceleration. And therefore, if I get t on its own there, that's going to be 4a plus g over 2 plus 2 root 3g. So that's my equation 1. So just redrawing that resolved diagram so it's a little bit cleared there up in the top corner because it was a bit too small. Okay, so in part, the next particle is our 8 kilogram. So we have our 8 kilogram, and if we look at the forces acting on that, so it's individual force diagram. Well, we have the tension acting in an upward direction, and the weight acting in a downward direction. So gravity acting on the block gives it its weight, so that's our 8g, and it is accelerating in a downward direction. So therefore, if we're looking at our net forces, will equal to our mass times acceleration. So there are only two forces here, our tension and our weight. So because it's accelerating down, our leading force is the weight and the opposing force is the tension. So that will be 8g minus t is equal to m times a. So again, if I rearrange there to get t in its own, I get 8g minus 8a. So I now have my second equation in terms of t. So I'm going to equate 1 and 2. So that'll give me 4a plus g over 2 plus 2 root 3g is equal to 8g minus 8a. And if I bring all the a's to the left-hand side, that gives me 12a. And if I bring everything else to the right-hand side, that gives me 15 minus 4 root 3g all over 2. And therefore that gives me a is equal to 15 minus 4 root 3 over 24 times g, or in decimal it would be 3.296 meters per second squared. Okay, so we're looking for the tension, and it's going to be correct to the nearest whole number. So I'm going to stick with my third form until the end. Okay, so we now have a. So we're going to sub that into one of our equations. So I'm going to sub it into 2 to find tension. So that gives us t is equal to 8g minus 8 times 15 minus 4 root 3 over 24 times g. So if I simplify that, that gives me, that gives me t is equal to 9 plus 4 root 3 over 3 times g. But of course we want to correct two decimal, or the nearest whole number. So to correct the nearest whole number, which of course is 52 as they asked us to show. Okay, so then the second part of the question, if we go back, says how far has the block moved up the plane after 1 second? So it's important that we note that the system is starting from rest. In other words, initial velocity is 0, and we're seeing how far has it moved up the plane after 1 second. Okay, so let's mark that as part 2. So what do we know? Well, we know the initial velocity is 0. We know our acceleration, as I said, in decimal was 3.296. That's meters per second squared. And then the time is 1 second. We want to know how far has it gone. So we have UAT and we're looking for S. So it's clearly going to be our equation S equals UT plus a half AT squared. And therefore S is equal to U times T plus a half times A times T squared. And therefore S is equal to 1.648 meters. Okay, so the next part of the question then says, well, after 1 second, so we know how far it's moved in 1 second, and then we're told the string is cut. So if the string is cut, well, what's going to happen? So we have to see, well, does the block actually reach the pulley or not? So in other words, is there enough momentum there for the 4 kilogram block to actually reach the pulley? So let's see. Well, we know what the initial velocity was when it was starting from rest. So we really need to know what's the initial velocity when the string is cut. So the initial velocity from when the string is cut will be the final velocity after 1 second. So therefore we can work out the final velocity here using our v is equal to u plus at. Initial velocity being 0, acceleration being 3.296 times 1 second. So in other words, the final velocity just as the string is cut now becomes the initial velocity. So we say after the string is cut, well, what do we know? Okay, well, we know that the initial velocity is now going to be the 3.296 meters per second. We know that its final velocity will be 0 because obviously it's going to be pulled up the plane, and obviously what will happen is it'll go up the plane and then it'll instantaneously stop before it starts to slide back down the plane again. So we're looking at the point of when it stops just before it changes direction, and we want to know is that at the point where the pulley is? In other words, does it reach the pulley? Now, what is its acceleration going to be? Well, we don't know, so we have to work that out. We want to know how far is it travelling. So the acceleration, we can work that out, right? So what we have to look at is when the string is cut, there is now no tension in the string. So if there's no tension in the string, well, what does that mean? Well, F is equal to ma. And if we go back to our previous equation, right, we could see we had tension minus F minus W equals our ma. But we're now going to have no tension here. So that equation is now going to become minus g over 2 minus 2 root 3 over g is equal to 4a. So our tension minus our weight. So in other words, we're left with minus g over 2. And what do we say? Minus 2 root 3 is equal to 4a. If I just move that down. And therefore that allows me to work out the acceleration when there's no tension. So that if I write it as a decimal, because obviously we're keeping everything in decimal form here now at this stage, we have minus 9.712 meters per second squared. And obviously that makes sense because if it's going up the block just at the point, it's going to obviously begin to decelerate. So just before it comes to a stop. Okay, so what can we do with this then, right? So we now know A, so I'm going to put this back over here so we can see what information we have. So we have minus 97.12 meters per second squared. So UVA is what we have, and we're looking for S. So clearly we're going to be using the formula V squared equals U squared plus 2AS. So if I sub in my values, I have 0 squared is equal to 3.296 squared plus 2 times minus 9.712 times S. And if I rearrange that, then To get S on its own, well, that gives me 0.559 meters. Okay, however, that's the distance it's travelled after the string has cut. So after string has cut. And what has it travelled up until the point where the string is cut? In other words, what is the total distance travelled before it comes to rest? Well, it had travelled 1.648 we had worked out. So look, where was that? Up here. So we had 1.648 here. And therefore, I must add that on to 0.559. And therefore, my total distance travelled is 2.207 meters. And of course, if we go back to the start of the question, well, how far from the pulley was it? Well, it was a distance of 2 meters from the pulley. So therefore, if it has travelled a distance of 2.207 meters, then yes. Hence, distance travelled is greater than 2 meters. Therefore, it reaches the pulley. Okay. All right, so where is our breakdown of marks for that? So we had 10, 20, so 30 mark question. And we had 5 for setting up our first equation, 5 for setting up our second equation. We had 5 for getting our tension out correctly, so 15 marks for the first part of the question. Then we had to work out how far it had travelled, which was 5 marks, so it was 20. And then looking at part 3, I should say part 3 there, sorry. Getting our acceleration out was 5 marks, and our statement then at the end and finishing off and concluding in total was 5 marks. Okay.